There are not many trains running up here at the minute. I'm currently quite far through, I think, a process of switching from using CMRI to MQTT for accessory control. It's gone well so far. I got through turnouts, I got through sensors, and the last major hurdle, I suspect, before getting it all connected up here are shift registers, both shift in registers and shift out registers. The way CMRI worked was perfect for shift registers because it worked in bytes, and shift registers have 8 pins on them that can have 8 different accessories connected to them, and when you call that data in from the shift in register into the Arduino, you get a byte that contains effectively 8 binary values for the 8 things that are connected to the 8 pins. CMRI works in bytes, so you just pass that byte into CMRI and you're done with. And it works pretty much very similarly the other way with shift out as well. MQTT doesn't work like that. It works on individual values, so I can't just grab a byte from a shift register or a byte from MQTT and send it on. I've got to pull those bytes apart, I've got to work out what's in them, and then I've got to send the right value to the right LED on out, going out, or coming in. I've got to get the value, I've got to get inside it, I've got to work out if it's changed, and then I've got to send it to MQTT if it needs to, and that's a little bit more complicated. I really do quite like shift registers as well. They certainly bring with them a couple of benefits. The obvious one is they increase the number of input or output pins, depending on whether you're shift in or shift out, available on an Arduino. It takes 3 or 4 cables to come out of the Arduino into a shift register, and then that shift register offers you 8 outputs, but it also gives you the opportunity to chain from one shift register to another, which means you without spending any more pins on the Arduino, you're extending almost limitlessly in the realms of this loft how many inputs or outputs you have. And it might not be entirely apparent from this picture, but they do give me the opportunity to tidy up the cables a little bit as well, because as the sensors kind of all head out down in that direction, there are sensors that are down here, say all of these green ones here, that are still plugged into the Arduino that I was pointing at before, but at this point they're probably 1.5 meters, 2 meters away from the Arduino, and each of them takes 3 cables, but I don't have to drag each of those 3 sets of cables 2 meters back to the Arduino. I just have to plug them into a shift register that's located underneath that baseboard. So it really does save on a lot of cabling, and if I'd kind of thought of that when I was starting, I might well have had less of a rat's nest down at the Arduinos than I actually have. Probably worth pointing out as well that these shift registers come in lots of shapes and forms. The actual shift registers are those chips there. They're shift out registers, I think. And the first lot I bought just came as those chips, which scared the life out of me. I did buy these breakout boards for those, so I've got something I can solder the chips on because they're just easier to work with than as a bare bone chip. But also for a pretty reasonable price, I think it works out about £1 each. You can buy these breakout boards that come with it soldered on already and fitted. These are the shift, if I can focus this, the shift out registers. I think the part number of the actual chip is printed on the board. It's that number that I can't quite focus on down there. I think it ends 95. So anything that ends 95 is a shift out register. I'll paste these part numbers because they're quite useful into the description. They come like this as kind of connected boards, and you have to solder the headers on. This is a shift in register, and it ends in 65. I think that's the number that I can't focus on down there. They have slightly different pin outs down here as well, but again, the breakout boards, sometimes the shift out boards are purple. The color doesn't really matter. It's this part number that's printed on them, the 951 for a shift out register and the 65 number for a shift in register. Hopefully then, some very, very brief background on binary. Let's start with decimal. This is the decimal number system, and it has 10 digits available to it. The highest value one being 9. So and it has column headings that go up in multiples of 10. So 10 ones are 10, 10 tens are 100, and so on. So the highest value number is 9. If I put that in that column, 9 ones are 9, so the value of this is 9. But if I need to add 1 to 9, I run out of digits, so I get rid of that 9. I put a 1 in the tens column, and I put a 0 in the ones column, and that's decimal. That's how it works. A binary is exactly the same, except the column headers go up in multiples of 2, and there are only 2 digits available. So if I've put a 1 in the 1 column, that's as far as I can go. So if I need to increase it to 2, I put, again, the same as I would with decimal, I put a 0 in there and I put a 1 in there. And so it goes on. And there is only ever, in any of these systems, one way of representing any particular number. So if we take 9 as an example, I'd put 1 in the 8 column and I'd put 1 in the 1 column. That equals 9, and it's the only possible way of representing 9 in binary. As far as the shift register is concerned, these represent the 8 pins of the on the shift register, and I think they kind of go A, B, C, D, and so on. But they also go, as far as I'm concerned, what I'm using these shift out registers for, when we get to them, is signals. And the signal LEDs are organized, I think, green, yellow, red, green, yellow, red, and then these two aren't used because they wouldn't fit a whole other signal on them. So if we take into account that this is where each coloured signal is placed, you can see here that currently a value of 9 on that shift register, a decimal value, integer value of 9, would represent green being on one signal and green being on the other. And if a train runs through a green and that goes to red, then this goes to 0 and this goes to 1. So that would be a value of 33. And it could only possibly be a value of 33. And if you took 33 and tried to feed it into that shift register, you would only ever come up with 0, 0, 1, 0, 0, 0, 0, 1. Back into the code then, and let's focus on shift in registers first. So shift in register can potentially hold 8 sensors, and it can read the values from those sensors and feed them back into the Arduino. So it's a little chip with 8 pins, a few others doing other things, but 8 legs, 8 pins that are connected to the output of 8 sensors. And I did a video recently on sensors and kind of outlined the need with sensors. We have a responsibility in the script to constantly monitor the state of the sensors, compare that to the sensors, and each time we read those sensor values in, we have to have stored what those sensor values were previously so that we can detect whether that sensor has changed or not. Because we don't want to pummel MQTT with all these messages about the state of a sensor if the state of a sensor hasn't changed. There's no point in sending 80 messages a second to 8 MQTT saying this sensor is the same value as it was previously. So we monitor the state of those sensors, we detect when the sensor changes state, and that's the trigger we use to send the message to MQTT to say there's been an update to this sensor. And it's much the same with shift in registers, in that the only thing we're going to do differently is we're going to read them from the shift register. But again, I felt it was easier and perhaps less confusing in the code to create a class for a shift register. And again, I mentioned in the sensor video, a class definition can contain any other object, just like an array can or anything like that. So my shift registers, really the definition of them kind of describes what they are. They have 8 sensors on them. They potentially have, well, this is a shift register, I'm going to use this class for either shift in or shift out. So it could have 8 sensors on it. If it's a shift in register, it could have 8 LEDs on it or other outputs if it's a shift out register. And we have a char value there, could be a byte, could be an integer, doesn't really matter, holding its previous values. And going back to that binary thing again, its previous values can be held in 1 byte, because a byte is equal to 8 bits, so it can hold any integer value that would represent those green, yellow, red values. Back into the main sketch and down to the loop void, and here's where my sensors were before, and I was saying for every sensor that you're aware of, update the sensor. So I've got a feeling Shiftin is going to be very much the same, but that's just calling a void that must be further down here somewhere, which I'll probably miss. Sensor process Shiftin, here we go. So it does the Shiftin stuff, it sets the pins, gets ready to read the data in from the shift register. So that's just kind of opening the gates, really, these right into the shift register pins, saying to it, right, I'm ready to read all your values in. And it goes through number of shift registers, back into a loop again for each shift register that you're aware of, read in from that shift register. And I did a video previously on how when you read in from a shift register, if it's in a chain, when you kind of empty the first shift register, you can see that empties it, and the values that are in the next one along in the chain sort of fall into the one that you've just read, so you can just keep reading one after the other. So we're reading, we're shifting in, and we're writing that into a data byte. And then we're saying, because that shift register, it doesn't really matter at this stage that it holds 8 binary values, because we know that those 8 binary values can be represented by 1 integer or byte or char, whatever we have to be reading it into. So all I'm saying here is in this one statement, we're saying if have any of the 8 values on that, or any of the 8 binary bits on that shift register changed. If they have, we're going to have to do something with the inputs. If they haven't, just carry on, it's fine, none of them's changed. So assuming they have, we're going to go and do something with the shift inputs, and then of course once we've done that, we're going to set the previous values to how it currently is, so that we're always on track with what the current value is. So update shift inputs, and this is where I found really some a really useful Arduino library function. So what's happening in here is it's saying we know if we get into this void, we know that something has changed because the previous integer value is different to the one we've just read. So at least one of the bits in this shift register has changed. So we say, okay, then we know that this shift register, this byte that we've been sent contains 8 binary values. So we go through, right, let's have a loop that goes through 8 times and use this very useful function here, bit read. Bit read, what it says is you pass the integer that you want it to read a bit from, and the index from which, going back to that 32 8 16 column representation of a binary number, which column you want to read from. So it's going to start from the end one, and it's going to go through all 8 bits in this byte. It's going to pull the previous one out as well. So here it's comparing the one it's just read, effectively the pin on the shift register is just read, compared to what the pin value was previously. And if it has changed, send a message to MQTT to say this sensor value has changed, and it's going to go through all 8 pins and check them, because it knows at least one of them has now changed, and it will update each one that has changed in MQTT. And on to Shiftout then. And there is another small complication with Shiftout, really, in that going back to this binary representation, it's not possible with a shift register to say to it, just update pin 8. You know, if say green here goes to yellow, green on column 1 goes to yellow on column 2, I can't, there's no way to send a message at shift register to say just change the light on pin 1 and just change the light on pin 2. You have to send a message that says change. You can only send a byte in, so that byte has to contain a representation for all of those columns. So the complication here with shifting out is we have to keep a log of what all of the values in each of these shift out registers are, because we'll only get an input from MQTT potentially for one of them. A green light has gone out, or maybe 2 of them if we're talking signals. A green light has gone out on pin A and a red light has come on pin C. So in updating pins A and C in a message to the shift register, we have to make sure that when we put them into a byte, that byte contains the correct representation of all the other signal lights that are on that, because we haven't had an update message for them from MQTT. So we need to know what they were previously, so we can just take the two updates and merge them into that byte in a way that will maintain the state of any LEDs that have not changed as part of this update. So again, just to try and maybe make the code a little bit more understandable and readable and memorable for me when I come back to it as well, because I tend to forget what I've written very quickly, I've created a class for an LED. It's very simple, really. All it has in it is a string that tells me it's JMRI ID. I have to know that because that's the only thing I've got to identify it back when I get a subscribed message from MQTT from JMRI through MQTT. All I'm going to get from it is JMRI ID and whether it's on or off. So I need to be able to take that message and match it to a pin on a shift register. So the start point with that is to have JMRI ID against these LEDs. And then if I go back to that shift register definition here, we have a list of LEDs on there. So that's kind of starting to create the framework we could use to match up a message from JMRI to a shift register and a pin. And the definitions are down here at the bottom, and they are getting quite long and frightening. Another complication is, by default, in fact the only way that JMRI will deal with signal heads and the LEDs for them when they get set up, is it uses turnouts. Although it has a lights table, it doesn't use them for signals if you create them in the default way. So I also need a way of managing when I get a message in from JMRI to say track/turnout/ID has changed. I need to know whether that ID represents a turnout, for which I'm going to have to go through PWM and set PWM values, or it's an LED which is just on or off. So that needs to be managed as well. But here are my definitions for the shift out registers, and it's all very simple. I've got two shift registers, so there are two elements in the shift register array, and each of those elements in the shift register array has just 6 LEDs on it, because I leave 2 pins blank because it just holds 2 signals. And then they have the ID of the JMRI ID that matches up to the LED that's on that particular pin. And the very rudimentary way that I am identifying whether, when a message comes in, whether it's a turnout or an LED, is to simply have an ID threshold. So anything under 1041 will be treated as a turnout. Anything with a number over the value of 1 or equaling 1041 or over it will be treated as a shift register pin. So down here where we are processing incoming messages, there's an if here that gets us into a condition where we've received a message that does contain the word turnout. We get and end up with an integer representation, numerical representation of the ID that was part of that message. So then we could say, okay, if the ID value is less than the output threshold ID, which was 1041, then treat it as a turnout and go through all the turnout PWM stuff. Otherwise, then we have to assume we've got an LED, so we'll treat it as an LED. What we do here then, what we're trying to determine, we know we've got an update to an LED value. We know that what we're going to end up doing is updating a pin on a shift register to turn an LED, a signal light, red to off to green, whatever it happens to be. So the first thing we need to do is identify, we've got an ID, we know that JMRI ID 1049 needs to be switched on. But the first thing we therefore need to do is find out which pin on which shift register JMRI ID 104 whatever it was, 9 is on, which is why we've got those JMRI IDs against the class. So it just has to go through them one by one, and it has to say, are you the one I'm looking for? Are you the one I'm looking for? When it does find the one it's looking for, it sets a couple of values. So it says, right, okay, the pin you're looking for is on this shift register, it's on this pin. And then there's a couple of breaks, because once we've found it, we don't need to carry on through those loops. So it just gets out of that loop. Make sure it's found them here, because it might have gone all the way through the loop and not found them. If it has found them, again, it uses thrown and closed values, which isn't representative really to LEDs, but that's what it used. Thrown is 1, closed is 0. So we then say, right, okay, get me the previous values from this shift register that we know the pin is on. We know this is the shift register. We know this is the shift register that we need to change on. So we need to get the previous values, because when we update this shift register, we need to update it where in a manner where the pins that haven't changed have the same value when we send that byte in as they did before. So again, we have this nice opposite kind of Arduino function called bitWrite, and what this is saying is take the previous integer value, whatever it was, 9, that was on this shift register, look at pin, whatever the pin index was that we found the match on for the JMRI ID, and update it to what the new value is, leaving all of the other pins bit values effectively with the same value, so that a red light on the other line stays red whichever the other signal is being managed. And then it goes to the shift register. Now this might be a little bit more cumbersome than possibly it is, but to be on the safe side, the way I've written the code at the minute is, because the shift registers are chained together, and the change I've made might be on shift number 3 down at the end of the chain, I'm just going to shift all of the shift registers back out again, because we've written and updated previous values on here. We haven't changed the previous values of any of the other shift registers. So down to process shift out, presumably would be down here somewhere. Here it is. We're simply saying we're doing a reverse I loop here as well. So we're starting at the end, because we need to go out in reverse order. Usually the lowest ID, the pins 1041, the one with the lowest JMRI ID, will be on the closest shift register. So we actually need to push these shift register values out in reverse. So start with the highest numbered shift register, send that one out, and then reduce your index by 1, and go backwards down the list, so that the lowest ID shift register is the last one to be sent out, and will therefore sit in the closest shift register, whereas the shift register with the highest JMRI ID LEDs on it will have been pushed along the chain each time we pushed a new shift register value in. And that is shift in and out. Here on the ever deepening project Workbench, then there's an Arduino that's plugged into the computer through the USB. That's just for serial debugging and console output, connected to the network with the Ethernet dongle. We have a shift register coming out of it somewhere, 3 sensors plugged into it in pretty much random pins, and there's also a sensor floating around that's directly connected into pin 2. So let's see if they will all work. So in my code, I have defined a shift register here, one shift register with 8 sensors on it, 8 inputs on it. There are actually only 3 sensors connected to the shift register, but that shouldn't matter. The others will just stay inactive. And the 8 sensors defined on the shift register have these JMRI IDs from 1041 to 1048. And then in my JMRI sensor table, I've defined those sensors from 1041 to 1048, so they have the same ID and should be matched up by the code. So now I guess it's just a case of moving a sensor and seeing what happens. So I'll start with the one I can reach more closely. That's good. So it's saying in the console, it's saying 1046. If I look over at 1046 in the sensor table, that's moving. That's good. What's this one? This is moving 1044. Is that moving 1044 in the sensor table? Yes, it is. And can I reach or even see the third one? There it is. Has it lost its wire? No, it's still working. It's making a mess now. But 1041 and 1041 is moving if the wire is still connected. I've got a feeling I pulled a wire out of that one. No, it's still moving. 1041 is still going active and inactive. And as a final test, somewhere literally hanging around, I have a directly connected sensor. This one's direct into pin 2 on the Arduino. That's working too, and that's moving sensor 1001, which was also defined in the code. So again, looking good. Hopefully a very similar test with the shift out registers then. I've defined a shift out register here with 6 LEDs on it to kind of simulate the signals from 1041 to 1046 in the code. Remember that 1041 threshold that tells the code whether it's going to treat it as an LED or as a turnout. And in my test MQTT profile in JMRI, I've actually ended up creating accidentally 8 of these, but 6 of them are the ones that I think will actually garner a response from the code. And it might be a good idea as well to just test the turnouts to make sure they get treated as a turnout. So anything below 1041 is a turnout, anything above 1041 or equals 1041 is an LED. So let's try and change a couple of these. So it's looking good. I can see this number here is kind of the important one, because what I'm looking for is it maintaining the value. I'm only changing one LED here, but I need it to insert that change effectively into this bit array, and it does look like it's doing that. If I go down and change 6, I can see it's going from because if I'm changing 6, it's kind of the leftmost one here, because it leaves off any leading zeros. So I can see that value is changing. It's kind of adding a 1 and replacing it with an invisible 0. And if I go and change number 1, I would expect this bit here to change, but all the others to stay the same. And it looks like they are. If I go and add the 6th, which is the last one again, that is looking good, and it's treating them all as LEDs because it's saying looking in shift registers for that ID. So let's just try a couple of turnouts and make sure they get treated as turnouts. That's looking good because I've got PWM values on here. They're actually set to move in slow motion, so there's probably not much visible on the camera, but something somewhere might possibly be moving there. It never quite works out this way, but I'm hoping that that's the coding done. It looks good on the Workbench. It's sort of doing what I want it to do. So the next step is the daunting one, really, of uploading it onto one of these, ripping out RS485, connecting it to my live JMRI profile, backing it up first, and seeing if I can actually, on the layout, make that transition from CMRI and RS485 to Ethernet and MQTT.